By the end of this video, you'll know what FreeToken really changes, why the 753 billion parameters on one workstation headline is both impressive and easy to misunderstand, and when you should choose it over Llama.cpp, vLLM, SGLang or Unsloth. FreeToken is not a model. It is an edge-native serving engine for sparse mixture of experts models. In the AI stack, it sits below your apps and OpenAI-compatible API, but above the GPU, CPU, system memory and PCIe link that execute every token. Here is the crucial distinction. Total parameters are not active parameters. A sparse MOE model owns a huge pool of expert weights, but its router selects only a small subset for each token. FreeToken keeps the full routed expert pool in host DRAM, places non-expert weights and a changing expert cache in VRAM, and moves computation across the machine. So GLM 5.2 at 753 billion is possible on one workstation GPU, but the cited system also uses a 96GB RTX Pro 6000 and substantial host memory. This is one workstation, not one isolated graphics card. It is an expansion of usable capacity, not magic compression. Why is this hard? During pre-fill, thousands of prompt tokens can touch almost every expert, turning model sparsity into a massive PCIe transfer. During decode, expert choices change token by token, so a fixed placement gets stale. And consumer CPUs read system memory far more slowly than modern GPUs read VRAM. Traditional offload can leave either the GPU, PCIe link, or CPU underused. FreeToken reframes the problem. Do not ask only whether the model fits in VRAM. Ask how to schedule the active work across the entire memory hierarchy on this specific machine for this specific phase of inference. The engine uses three coordinated mechanisms. First, during prefill, it double buffers complete expert layers. While the GPU computes one layer, the next can stream across PCIe. For agent workloads, semantic anchors preserve reusable recurrent and KV state around boundaries such as tool calls and thinking blocks, so an edited conversation can recompute only the changed suffix. Second, during decode, a global least recently used cache keeps frequently selected experts in VRAM. When an expert misses the cache, FreeToken does not always copy it to the GPU and does not always run it on the CPU. Its Q-star policy measures effective PCIe and host memory bandwidth, then splits misses between both paths. The partial outputs merge exactly. The model router is not approximated. Third, FreeToken can rebalance VRAM between the export cache and the KV cache at safe scheduler points. More cached experts improve decode, while more KV space supports longer context and more concurrent work. The important idea is the coordination. Streaming, caching, CPU-GPU execution, and memory budgeting become one policy instead of separate knobs. That is where FreeToken's contribution sits. The upside is practical access. The paper reports 77 to 83 tokens per second for Qwen 3.6-35BA3B and 22 to 25 for DeepSeek V4 Flash on an RTX 5090, with 1.5 to 2.3 times higher decode throughput than its selected edge baselines. It also reports 39.3 tokens per second for a 35 billion MOE on an 8GB laptop GPU and 14.9 for GLM 5.2 on that workstation. A Reddit tester reported roughly 100 tokens per second for a 20GB Qwen build on a 16GB RTX 5080. These are promising signals, but the paper results are author-reported and the community result is one configuration, not a controlled benchmark. Quantization, prompt shape, output length, tuning and hardware must match before any speed comparison is fair. There is now a Windows desktop app, and the onboarding is polished. Model library, chat, local API endpoints, and launchers for coding agents. But the official page labels this build beta. In our captured walkthrough, the interface opened while the engine remained uninstalled. The installation attempt then rejected Q130 as an invalid Torch backend, and the wheel install failed. That is one observed attempt, not proof that every Windows install fails. It is useful evidence of where the product is today. Approachable interface, young packaging, and some setup friction still to expect. For developers, the repository documents a separate UV path. Start with the requirements: Linux, x86-64, an NVIDIA GPU, driver 580 or newer for CUDA 13, Python 3.10 or newer, and the CUDA toolkit with NVCC on your path. Then create and activate an isolated environment, UV venv, followed by source.venv/bin/activate. Install the accelerated package with UV pip install FreeToken Axshell. On first use, CUDA kernels are compiled just in time, so the first launch can take longer. If you want the editable source build, clone the repository, enter the FreeToken directory, create the same environment, then run UV pip install -e.axshell. Finally, verify with ft-version. Before serving a model, run ft-bench bw once per machine. That benchmark measures real host memory and PCIe behavior and writes the hardware profile used by the automatic hybrid policy. This calibration step is not ceremony. It feeds the scheduling idea we just explained. Now, launch the server with one required argument, ft-serve-model, followed by a local model path or Hugging Face repository ID. FreeToken resolves D-type, attention backend, MOE backend, cache sizes, CUDA graph sizes, and parsers from the checkpoint and GPU. Wait for the log that says the API server is ready on 127.0.0.1, port 1919. Check the served model with a GET request to /v1/models, then send a normal OpenAI-compatible chat completions request to the same base URL. The server also exposes responses and Anthropic-compatible message endpoints. For a quick terminal chat, use ft-shell. Add --model if you wanted to start the engine and chat in one process. For coding agents, the launcher supports Claude, Codex, OpenCode, OpenClaw, Hermes, and more. Start cautiously with ft-launch codex --dry-run. That previews the provider configuration and command without touching anything. Remove dry run when the plan looks right. The practical stack is now visible. Your agent speaks a familiar API, FreeToken schedules the model, and the local machine supplies the compute. The remaining trade-offs are substantial. The CLI path is currently centered on Linux, NVIDIA, CUDA 13, and recent drivers. FreeToken needs enough host RAM, good DRAM bandwidth, and a capable PCIe link. A weakly balanced system can erase the advantage. It specifically helps sparse MOE models, not every dense model. Default maximum running requests is 4, so this is not evidence of data center scale concurrency. Public issues report a KV budget case where prompts larger than the pool silently queued and a prefill hang on one RTX 4060 Ti setup. These are individual reports, not universal failures, but they reinforce the same rule. Test your exact model, quantization, context length, prompts, and hardware before trusting a headline. The clean comparison is by job. Choose FreeToken when a sparse MOE is larger than VRAM and you want one NVIDIA workstation to use GPU, CPU, DRAM, and PCIe adaptively. Choose Llama.cpp for the broadest local portability, mature GGUF tooling, and flexible CPU-GPU inference. Choose vLLM for high-throughput GPU serving, continuous batching, and distributed production. Choose SGLang for high-performance agent serving, prefix reuse, structured generation, and cluster scale. Unsloth is mostly upstream, fine-tuning, quantization, and exporting models into serving engines, so it often complements these tools rather than replacing them. The FreeToken paper did not benchmark vLLM or SGLang directly. If FreeToken holds up, the stack changes from "does it fit in VRAM" to "how should this token use the whole machine?" It will not erase the other runtimes. It creates a sharper category, adaptive workstation scale MOE serving. Watch the independent benchmarks, compatibility, and issue velocity. But the systems idea is real and worth paying attention to.